Great, thank you very much for the introduction and the invitation. And what is that? This meeting is being recorded. Okay. Yeah, I'm very happy to give a talk in your seminar, and I will tell you about the KKM theorem, a few generalizations of it, and at least 3 applications. So let me start by reminding or telling you what is the KKM theorem. So we have the n-1 dimensional simplex that we think of embedded in Rn in the usual way. So it's the convex hull of the standard basis vectors in Rn, or the set of n tuples with coordinates that are non-negative and sum up to 1. And so let us introduce the KKM theorem. It tells us that suppose that we have n sets that are either all open or all closed, and these are subsets of the n-1 dimensional simplex, and they cover the simplex, but in a nice way. So here is the description of this nice covering condition. Vertex 1 must be in the set R1. Vertex 2 must be in the set R2, and the edge 1, 2 must be in the union of R1 and R2. And similarly, vertex 3 must be in R3, and the edge 1, 3 should be in the union of R1 and R3, and so on and so forth. And if we want to write this condition, then it is that for every face of the simplex, every face sigma is contained in the union of the Ri's, where I is a vertex in sigma. If we have such a covering of the simplex, then the KKM theorem promises us that the intersection of all the sets is not empty, as we see here in this small example. And this example may be misleading because I picture the sets as connected sets, but there is no such condition. They can be any such sets that are either open or closed and satisfy this covering condition. Okay, so this theorem was proved by Knaster, Kuratowski and Mazurkiewicz in 1928. It is reminiscent of Sperner's lemma, if you are familiar with, and it is very close to Brouwer fixed point theorem. All of these results are very easily proved one from another. But since then, it had a lot of generalizations and a lot of applications. So here is a partial list of generalizations. There was a colorful KKM theorem of Gale in 82. We have a theorem of Shapley where there are more sets than vertices covering the simplex. We have a polytopic version of Shapley's theorem from 94. We have a sparse colorful, whatever that means, theorem of Soberon that generalizes Gale's colorful KKM from 21. And there are also kind of like a combination of these. So there is a colorful polytopic Shapley's result that was proved by Florian Frick and myself in 2019. And also recently with my student Daniel McGuinness, we proved the sparse colorful version of this theorem. So I will mention some of these results in this talk, but first let us jump into a first application of the KKM theorem, and this is about piercing sets in the plane with lines. So let F be a finite family of compact connected sets in R2. And we say that F can be pierced by K lines if there are K lines or whose union intersects every set in the family. And we will also say that the family has a line transversal if it can be pierced by one line. And we say that F as the tk property for some integer k if whenever I pick k sets in F, I find a line transversal for these k sets. So here is an example of a family with the T3 property. So I think about these 4 squares as convex squares, so they are filled in. And I claim that they have the T3 property because every time I pick 3 squares among these 4s, then I can find a line that pairs them. And clearly, if a family has the TK property, then it also has the TK minus 1 property, because if every K sets are pairs by line, then every K minus 1 sets are pairs by line. So as in the Heli-type theorem or PQ-type theorems, we are given some local property on the family of sets that it has the TK property. Every time I take K sets, I know something about these sets, in this case that they have a line transversal, and I'm looking for a global intersection property. So I'm looking for how many lines are needed to pierce a family with the TK property, if at all there is such a bound. So this question was studied since a while ago, where Santayo showed that no matter how big K is, you can find an example where the family has the TK property.
Sorry, could you repeat what is the TK property, please?
Yes, the TK property is a family of compact connected sets in the plane will set to have the TK property if every time I look at K sets among this family, I find the line that intersects all these K sets.
Understand, thank you.
So here is an example with the, so this example of the squares here has the T3 property because of this picture here. So Santayo proved that, or showed examples for any K of families with the TK property that cannot be pierced by one line. So at least 2 lines are needed. On the other hand, in 69, Eckhoff showed that the T4 property already implies that you can pierce the family with 2 lines. And this shows that this is true for any K greater or equal to 4, because if a family has the TK property for K greater or equal to 4, then it already has the T4 property, and therefore it can be pierced by 2 lines. On the other hand, if we look at the T1 or the T2 property, then it is clear that this will not give us a constant upper bound on the number of lines piercing the family, because you can look at the set of points in general position in the plane. So if the set of points has n points, then clearly it has the T1 and the T2 property. Every 2 points has a line passing through them, but you need n over 2 lines to pierce all the points in the family. So there is no constant bound. So the only question that remains open is what happens when K equals 3. And Kramer, so for a while it wasn't clear if there is a constant bound, but then in 75, Kramer showed that if a family has the T3 property, then it can be pierced by 5 lines. And Eckhoff showed that 2 lines are not enough. So here is an example of Eckhoff with, I think, 13 sets. So the triangles that you see here, and plus this disk in the middle. And you can check that it has the T3 property. Every 3 sets has some line passing through them, but you cannot pierce everything with 2 lines. And finally, Eckhoff showed in 93 that the T3 property implies that you can pierce the family with 4 lines, and he asked whether you can improve this bound to 3. If you could, then this would be best possible by the previous example. And this is what we proved with Daniel, my student, that the T3 property in the plane implies that you can pierce the family with 3 lines. Any questions about the statement of this theorem? All right, so the proof uses the KKM theorem. So I want to give you the proof now. So let F be a family of finite family of compact connected set in the plane with the T3 property. And since the set is finite and the family is finite and the sets are compact, I can rescale the plane such that all the sets are lie in some disk of circumference 1. So here is the disk with circumference 1, and I assume that all the sets in my family lie inside this disk. And I want to use the KKM theorem, so I have to introduce some simplex and the KKM covering of the simplex. So in this proof, our simplex will be only of 5 dimensions. So let X be a point in delta 5, and recall that this means that it is a 6 tuple of numbers x1 to x6 such that they are non-negative and sum up to 1. And now I will show you how each such point X corresponds to 3 lines in the plane. So first, X corresponds to 6 points on the circumference, on the boundary of this disk as follows. So the first point is just a fixed point, which I call 0, and this point will be state fixed throughout this proof. And then P1 of X is going to be the point that the arc length between P1 and P0 is exactly this number X1. And then P2 is the point of arc length X2 from P1, and so on. P3 is the point with arc length X3 from P2, and P4 is the point with arc length X4 from P3. And then we have P5, which has arc length X5 from P4. And since X is in delta, then the arc length between P5 and P0 must be X6 because the circumference here is 1. Okay, now X correspond to 3 lines as follows. So I connect P0 and P3 by a line, I connect P1 and P4 by a line, and I connect P2 and P5 by a line. And finally, let us distinguish 6 regions in this disk corresponding to X. So region Rxi is the region that is the open region that is bounded by the line Li, Li minus 1, and the arc between Pi and Pi minus 1. And I call the lines by the endpoints. I forgot to say that, sorry. So for example, this line is L1, but also L4. And this line here is L2, but also L5, and so on. So here is R1 of X, here is R2 of X, R3 of X, R4 of X, R5 of X, and R6 of X. And as you notice, some of these regions intersect. So for example, in this picture, I have that R1, R3, and R5 intersect in this small triangle in the middle. But we have R2, R4, and R6 that are pairwise disjoint. And if for some reason this point P3 was a little bit up here, then suddenly I would have had that R1, R3, and R5 would have been pairwise disjoint, and R6, R2, and R4 would have intersected. But in any case, it is a very simple lemma to observe that in any such configuration, either R1, R3, and R5 are pairwise disjoint, or R2, R4, and R6 are pairwise disjoint. And another thing I want you to notice is that if one of these coordinates in X is 0, then the corresponding region is the empty set, because I'm taking the open region that is bounded by the lines and the arc. Okay, any questions about the setting so far? Okay, so now I want to tell you how to define sets for the application of the KKM theorem. So we want to define a KKM cover of delta 5. So I need to tell you how to define sets A1 to A6. So X will be in AI if and only if the region Ri of X contains a set of F. So here is an example. Suppose this is X. These are the regions corresponding to X. And there is a set of F. Here it is in the second region corresponding to X. Then in this case, X will be in A2. And here is another picture. Suppose there is this set from F here, but another set here. So X will be in A2 because of this set, and in A3 because of this set, because it is in the third region corresponding to X. And in this picture here, I have a set here in the triangle in the middle. So X is in A1, A3, and A5 because of this set in the middle, and it is also in A2 because of the set here. Okay? Is this definition clear enough? All right. So let us assume first that I can find some X in delta that does not lie in any of the sets AI. Then here is X, and it is not in any of the sets AI. It means that none of the sets AI are, and none of the sets in F are in any of these regions, but they are connected. So they must lie on the lines corresponding to this X. So if X is not in any of these sets, then the three lines corresponding to X pierce all the sets in F, and we are done. Okay? So assume for contradiction that this is not the case. So for every X, X lies in some AI. Okay, so, or to say it differently, delta 5 is contained in the union of all the AIs. Okay, so I claim that in this case, A1 to A6 form a KKM cover of delta 5. So let us prove this. So we want to show that for every phase sigma, that is the convex hull of a subset of the vertex set, we have that sigma is contained in the union of the AI where I is a vertex in sigma. So let us take a set X, a point X in sigma, and we want to show that X is in this union of AI where I is a vertex in sigma. So if I is not in I, if I is not a vertex in sigma, then by the definition of delta, xi is just 0. So by our previous observation, Ri of x is the empty set. So Ri of x cannot contain a set of f. Okay, so x is not in AI. And this shows that x is not in the union of the AIs where I is not a vertex in sigma. But since we have that X is contained in the union of all the AIs, and it is not in the sets that AI that I is not a vertex in sigma, then it must be in the union of the AIs where I is in sigma. And we are done. Okay. So the only observation that we need here is that when xi is 0, then Ri of x is the empty set, and therefore it cannot contain a set of f. And I have also to show you that these sets are all open or all closed. So in this case, they will be all open because the sets are closed. The sets in F are closed. So if we wiggle a little bit the point X, so take something in the epsilon neighborhood of X, then the regions will be very much similar. So if a region contained the set of F before, then it will contain a set of the same set of F after this small wiggling. Okay, so we have all the conditions of the KKM theorem. So by the KKM theorem, all the sets AI intersect. So we can find an X in the intersection of all the sets. Here is this X, and here is the distribution of points corresponding to this specific X in the intersection. Then X is in A1 means that there is a set in the first region corresponding to X. X is in A2 means that there is a set in the second region corresponding to X, and so on. So there are sets in every one of these regions. In particular, there are 3 sets in the 3 pairwise disjoint regions that are either R1, 3, and 5, or R2, 4, and 6, as we mentioned before. But it is easy to observe that such 3 sets cannot be pierced by one line, because if there is a line piercing these 2 sets, then it must be on the right side of this line, but then it cannot be pierce this set. Again, an easy geometrical lemma that its proof is 2 lines. So we found 3 sets in F that are not pierced by a line, but this is a contradiction to the T3 property. So we are done. Okay. Any questions about this proof? So I think it was the first time where topological methods were introduced to this problem. And it actually gives us a way to generalize this theorem even more. So actually, what we can prove is a colorful version of this theorem. So we can prove that if we have 6 sets, sorry about these 3 here, should be 6, of compact connected sets in R2, and if we have the property that every time we pick 3 sets from 3 different families, then these 3 sets A, B, and C have a line transversal, then we can find an integer between 1 and 6 such that Fi is pierced by 3 lines. And this is a generalization of the previous theorem, because if you take all the families F1 to F6 to be the same family F, then you get back the previous theorem. Okay. And similarly, we can prove a colorful version of Eckhoff's result that the T4 property implies that you can pierce everything with 2 lines by taking, instead of 1 family, 4 families. So how do we do that? By just replacing in the proof the KKM theorem by the colorful KKM theorem of Gale from 82. So let me tell you by what is the colorful KKM theorem. So now instead, we still have the n-1 dimensional simplex, but instead of having 1 KKM cover of it, we have 3 KKM or n KKM covers of it. So in this picture here, we have the two-dimensional simplex and 3 covers of it, the red one, the blue one, and the green one. And so the KKM theorem tells us that the sets in each one of these covers intersect, but Gale tells us that we can find a selection of one set from each cover corresponding to each one of the vertices, such that this selection of sets, this colorful selection of sets intersect. So we can find a permutation of n elements such that the intersection of ai pi of I is non-empty, where the AIs, AIJ are our KKM covers. So I index by this little j here the different KKM covers that I have between 1 and n. Okay, so in this picture, for example, I have the green set corresponding to vertex 1, the red set corresponding to vertex 2, and the blue set corresponding to vertex 3 that intersect. And Gale promises us that this always happens. Okay, questions so far? So let me give you now another application. Third division of cakes. So the situation is as follows. We have a cake or some resource that we identify with the 0,1 segment. And we have n people that have a preference on this resource. And their preferences are subjective. So each one of them want different things from this resource. And every time I want to divide this cake between them. And every time I introduce some partition of the cake into n pieces, each one of the players can choose or must choose one or more pieces that he's happy with. So for example, suppose I introduce this partition, then in this partition, player green prefers the rightmost piece and blue and red prefer the middle piece. And suddenly if I give a different partition, then red and green want the left piece and blue still wants the middle piece. And what I'm looking for is an envy-free division of the cake, namely a partition of the cake into n pieces where each one of the players prefers a distinct piece. And the question is whether or under which conditions such a division exists. So the classical theorem of Stromquist and Woodall independently in 1980 tells us that if two conditions are held, and the conditions are that the players are hungry and that the preference sets are closed, then there exists an envy-free division of the cake. So what does it mean? What are these two conditions mean? So the first one means that in every partition of the cake, the players want a non-empty piece or a positive length piece because they are hungry, so they don't want to eat nothing. And the second condition tells us that if a player prefers piece I in a converging sequence of partitions, then it prefers piece I also in the limit partition. And the proof is just the KKM theorem. In fact, this theorem is the colorful KKM theorem. So I think that what happened is that Stromquist and Woodall proved the colorful KKM theorem 2 years before Gale using a different language. So here is how we do the translation. So every point in the simplex corresponds to a partition of the cake into three pieces, into n pieces. So the first piece is of length x1, the second piece is of length x2, and so on. And we use the preference, the preference sets of the players to define covers of the simplex. So we have n players, and these will correspond to n covers. So the set Ri in the red cover will be those partitions in which the red player prefers piece I. And similarly, Bi partition in which the blue player prefers piece I, and Gi partition in which the green player prefers piece I. And so here is an example. So here is a partition X, and I claim that it is in R1 because red prefers piece 1. It is in B2 because blue prefers piece 2, and it is also in G1 because green prefers piece 1. Okay. And what I'm looking for is an envy-free partition division of the cake, which is exactly an intersection of a point in the intersection of n sets from the n different covers corresponding to n different vertices. So the conclusion of the colorful KKM theorem is exactly what I'm looking for in the third division theorem. So what we just have to make sure is that the conditions of the colorful KKM theorem hold, and these are exactly the conditions of this theorem. So let us see that the hungry player condition is exactly the KKM covering condition. So here is an example. Let us look at the partition 1, 0, 0. So in this partition, the first piece is of length 1, and the second and third piece are of length 0. So they are empty. But since the players are hungry, then all of them choose in this partition the first piece, which means that this partition belongs to R1, and it belongs also to B1, and it belongs also to G1, which tells us that the vertex 1, 0, 0 is in R1, B1, and G1, which is exactly the KKM condition for this face, for this vertex. And this is true for any phase sigma that you take. So the hungry player condition is exactly the covering condition, and the closed preferences condition is exactly the fact that these Ri, Bi, and Gi are closed. So these are the conditions of the colorful KKM theorem, and therefore by the colorful KKM theorem, such a point exists, which is exactly an envy-free division. Okay? All right. So now we want to generalize this theorem in a few different directions. So the first direction is a very nice theorem of Soberon from 21, in which, so what Soberon does, he says that the fact that every player is hungry is very strong. And we actually can relax this condition and still get a similar result. So here is a definition by Soberon. N players are said to be K hungry if in every partition of the cake and in any selection of n minus k plus 1 players, at least one player among these n minus k plus 1 players prefers a non-empty piece. So if you take k to be n, then you get back the hungry player condition. Okay, so instead of demanding that every player is hungry. I just demand that every time I take n minus k plus 1 players, at least one of them is hungry. And what Soberon proved is that if we have n players that are k hungry and their preference sets are closed, then there exists an envy-free division of the cake among k of the players. So at least k players can be satisfied. And this is, of course, a generalization of the previous theorem by taking k to be n. And how we prove this? By replacing the colorful KKM theorem by a sparse colorful KKM theorem that Soberon proved. So here is the theorem. So now we don't have KKM covers, but we have sets A1 to AK that form what we call a weakly KKM cover of the K-1 dimensional simplex. So these family of sets, A1 to AK, are indexed by this J here, and J is an integer between 1 and n. And the condition is that every time we take an index set of size n minus k plus 1 among all those n integers, then the union of the corresponding sets form a KKM cover of the K-1 dimensional simplex. So each one of these families is not a KKM cover, but a big enough union of them form a KKM cover for any, so any big enough union of them. And big enough is taking n minus k plus 1. And then the conclusion is that we can find an injection pi such that the intersection of ai with index pi of I is non-empty for any I between 1 and k, which is exactly what we need if you translate back to the cake division language. And if we take k equals n, so then again we get the colorful KKM theorem. Now I want to tell you a different generalization of the KKM theorem. And the reason I want to do that is not because I just want to throw generalization at you, is because I want to be able to give you more applications. And for those applications, we will need more generalizations, and in particular, generalization of the KKM theorem for polytopes that are not the simplex. But first, let us introduce Shapley's result, where we have more sets than vertices. So here is Shapley's theorem. We have, again, the simplex in this case, the n-1 dimensional simplex, or here I wrote the n-dimensional simplex. And we have sets covering this simplex. But before, the sets were in the KKM theorem, the sets were indexed by the vertices. So we had, if we had the n-dimensional simplex, then we had n-1 sets A1 to an plus 1 corresponding to the n-1 vertices of the simplex. Here, Shapley allows us to index sets by any face, not just the vertices. And we have, again, a nice covering condition. So vertex 1 still should be in A1, and vertex 2 still should be in A2. But now the edge 1, 2 can be in the union of A1, A2, and A1, 2, the set that is indexed by this edge. And similarly, vertex 3 must be in A3, the edge 2, 3 must be in the union of A2, A3, and A2, 3, and so on, okay? So if we want to write this, is that every face tau is contained in the union of the A sigma, where A sigma is a subface of tau. Okay? And then the conclusion is it's not true anymore that all the sets intersect, as we see even in this small example. But what is true, that we can find a balanced collection of faces, sigma 1 to sigma m, such that their corresponding sets intersect. So what does it mean to be balanced? So informally speaking, it means that we can find weights on these faces such that every vertex of sigma is represented in the same weight. And formally, we can say that faces sigma 1 to sigma m are balanced if their corresponding barycenters convex the barycenter of delta. So here in this example that we had before, we see that A12, A13, and A23 intersect. And I claim that 1, 2, 1, 3, and 2, 3 are balanced because their barycenter have the barycenter of delta in their convex hull. Okay, so a restatement of the KKMS theorem is that given a KKMS cover of delta, we can find faces such that the intersection of the sets indexed by these faces is not empty, and simultaneously the barycenter of the simplex is in the convex hull of the barycenters of these faces. Okay, so again, not all the sets intersect, but a large enough and nice enough collection of sets intersect. And this is the description of what is to be nice enough and large enough. All right, so now we want a polytopal version of this theorem, and this is what Komiya gives us in 94. So Komiya observes that we can replace delta by any n-dimensional polytop, and we can replace the barycenters by any pre-chosen points in the faces, and still the theorem would be correct. So here is Komiya's theorem. So given a Komiya cover of an n-dimensional polytop P, and to be a Komiya cover is again the same thing. So every face tau of P is contained in the union of the A sigmas, where sigma is a subface of tau. And given any points y sigma in sigma, for any face sigma, then we can find faces sigma 1 of sigma m of P, such that the corresponding sets A sigma I intersect. And simultaneously, the point that we've chosen for the polytop is in the convex hull of the points that we've chosen for these faces. So let us see an example. Okay, here is a polytop, this rectangle. And here is a Komiya cover of this polytop. So I've taken all the sets to be empty sets, except for the sets that correspond to the vertices. So I have the vertices 1, 1, 2, 1, 2, 2, and 1, 2, and I have 4 sets corresponding to these vertices, and you can check that this is a Komiya cover. For example, this edge is in the union of the sets that corresponds to the vertices in this edge. And what Komiya tells us that either A11, A22 intersect, or A12, A21 intersect. So we have kind of like a seashore lemma, I don't know. In Hebrew, you would say that. So why this is true? why this follows from this theorem. So I showed you the sets. I have to tell you what are the Y sigma. So I'm taking still the barycenters to be the Y sigmas. And then, since this is a Komiya cover, the theorem tells us that there exist faces such that the intersection of the sets is not empty, and the barycenter of the rectangle, which is a point here, is in the convex hull of the barycenters of these faces. But since we have a non-empty intersection, we must have that this barycenter is in some convex hull of barycenters of the vertices, because only them have a non-empty set. And if we want this barycenter to be in the convex hull of vertices, then it must be that either we take 2, 1 and 1, 2, and maybe other vertices, or we take 2, 2 and 1, 1, and maybe other vertices. So in particular, either this happens or this happens. Okay, questions about that? All right. So what we proved with Florian is a colorful version of this Komiya theorem, the same as the colorful KKM is a colorful version of KKM. So let me state this theorem. So P is an n-1 dimensional polytope containing some point yp. Here is in the picture, the point is called 0. And suppose that we have n Komiya covers of P. So I have sets A sigma, where sigma is a face of P, and I have this index I showing I between 1 to n, so I have n such collections. And for every proper non-empty face sigma of P, I am choosing n points y sigma with this index I, where I, again, between 1 to n. And I don't even have to choose these points in sigma. I can choose them anywhere in the cone of sigma, where the cone of sigma is this cone that is the collection of rays that go through the origin and intersect this space. Okay. Then I can find faces sigma 1 to sigma n of P, such that a colorful selection of the sets intersect. So A sigma I from the first Komiya cover and A sigma 2 from the second Komiya cover and so on intersect, and correspond and simultaneously the point yp that we've chosen in P is in the convex hull of the colorful selection of points y sigma I. All right, so this is maybe a lot to digest, but we can use this theorem to actually prove a fair division theorem with multiple cakes. So let us introduce that. So again, we have n players, but now we have k cakes. In this picture, 2 cakes. And suppose this is I don't know, a lemon pie, and this is a chocolate cake. And every time, and both cakes are in the same party, and all the players want a piece from each one of them. So every time I introduce a partition of the first cake to n pieces and the second cake to n pieces, and all the k cakes to n pieces, each player chooses a k tuple of pieces. So for example, in this partition, the blue I've chosen this, the middle in both of them, the green I've chosen these two, and so on. And what I'm looking for is a partition of the K cakes into n pieces each, such that many players are satisfied, so that many players prefer pairwise disjoint K tuple of pieces. And this is the theorem of Neyman, Su, and myself in 2020, that if we have K case and n players, and we have this situation that in every partition, every player prefers or chooses his favorite K tuple of pieces. And if the players again are hungry, so the K tuple of pieces that they choose contain only non-empty pieces, and their preference sets are closed, then there exists a fair division of the cakes for at least number of players over K squared players. And this, I've written it with this omega notation because it depends on how many players I pick here. If they have some divisibility condition, then I will see here exactly K squared. Otherwise, I will see here a factor of 2, but it doesn't matter. So how do I prove this? I use the previous theorem, the colorful Komiya theorem, but instead of taking the simplex, which is the configuration space of partitions of one cake, I take the polytope that is the product of K simplices, and this is the configuration space of the partition of K cakes. And then I use the conclusion of the Komiya theorem together with some hypergraph matching theory in order to derive a large matching in the hypergraph that I get, which is of size P over K squared. Okay, so here is an application of colorful Komiya. I will give you another application of colorful Komiya at the end of the talk, which will be in around 10 minutes. Is that okay, Patrick? Good. But here is a sparse colorful generalization of this multiple cake fair division theorem. So as Soberon did in the case of one cake, we can do now in the case of K cakes. So again, there are K cakes, P players. Each player prefers one piece from each cake in any partition of the cake into n pieces each. But now not all the players are hungry, but large enough collection of them, in any large enough collection of them, one player at least is hungry. So every time I pick n minus k plus 1 players, at least one of them prefer a non-empty tuple of pieces. Then we can still ensure that we have a fair division to the same number of players as before. And this follows, as before, from a polytopic sparse colorful KKM theorem that we proved with Daniel that generalizes the colorful Komiya theorem. So it is what you expect it to be. If P is a K-1 dimensional polytope with some point chosen in it, and for every face you choose n points, and you don't have n Komiya covers, but you have a family of sets that forms a K weakly Komiya covers in the same sense that we had before. And then the theorem ensures that there is such an injection that gives us the conclusion that we want to get. Okay. Any questions so far? So the last thing I want to give you is another application, third application, and this will be an application of the colorful Komiya theorem of Florian and myself. And we will prove with it the colorful Kuratowski theorem of Brouwer. So the colorful Kuratowski theorem tells us that if we have d+1 sets in Rd, and each one of these sets convex 0, then there exists a choice of one point from each one of these d+1 sets that such that these d+1 points convex 0. So in the plane, here is an example. We have the red set of points, the blue set of points, and the green set of points. And you can check that each one of them has 0 in its convex hull. And I can find a choice of one red point, one green point, and one blue point such that 0 is in their convex hull. And now I want to show you, so there is a very nice proof of Imre of this theorem, but I want to show you now a different proof that follows from the colorful Komiya theorem. So I will prove it in 2 dimensions, but it works in any dimension. So I want to tell you, I want to use the colorful Komiya theorem. So I want to tell you what is the polytope that I'm taking, what are the sets A sigma that I'm taking, and what are the points Y sigma that I'm taking. So I'm taking a polytope that is fined enough such that 2 conditions hold. The first is that this polytope will have 0 in it. And if I look at the cone of any face, then it contains only at most 1 point from each color classes. So here, for example, in this sigma that we see here, it has one blue point, one red point in this cone, but it doesn't have any green point, which is okay. I just don't want to see 2 red points in the same cone. If I see that, then I'm just taking a finer polytope. So I will subdivide this face and wiggle a little bit to get a finer polytope. And the other condition is that I want this angle here to be less than 90 degrees, which also I can do by subdividing faces. Okay, so I told you what the polytope is. Now I will tell you what my sets are, A sigma, and what my points Y sigma are. So there are 2 cases. I'm looking at my sigma, and I want to tell you what is A sigma. A sigma of red, A sigma of blue, and A sigma of green. So A sigma of red, so I'm looking at the cone corresponding to sigma. If there is a red point in this cone, then I'm taking the hyperplane perpendicular to this point, and I'm taking its positive part intersection with my polytope, and this will be my A sigma red. And my Y sigma red in this case will be just this point, this red point in the cone. And similarly, I have a blue point here, so I'm doing the same for the blue. So I take the hyperplane perpendicular to this point. I'm taking the positive part of it intersection with my polytope, and this will be my A sigma blue. And my Y sigma blue will be just this blue point. And there is the case where in green, for example, there is no point, no green point in this cone. So in this case, I'm just taking a sigma green to be sigma itself. And I'm taking y sigma green to be the barycenter of sigma. So, okay, so now I've chosen everything I needed for the theorem. All I need to show you is that the condition of the theorem holds and that the conclusion gives us what we want. So the conditions of the colorful Komiya theorem hold because for every sigma, we have that sigma is contained in an a sigma I. So it is contained in the union of the a tau i's, where tau is a subtrace of sigma, right? Because in this case, sigma is just a sigma, and in the other cases, sigma is contained in the a sigma. Okay, and the sets are closed just by how I take them. So the colorful Komiya theorem conditions hold. So by the colorful Komiya conditions, I have sigma 1, sigma 2, and sigma 3 such that a sigma 1 red, a sigma 2 blue, and a sigma 3, this should be 3 here, green intersect. And simultaneously that 0 is in the convex hull of y sigma 1 red, y sigma 2 blue, and y sigma 3 green. So note that if I knew that all these points, y sigma 1, y sigma 2, y sigma 3 are the original blue, green, red points from the sets that I'm given, then I'm done, right? This is what I wanted to prove. So all I have to show you is that there are no kind of fake points that I added to the picture by taking barycenters. But this follows from this condition here, because if these sets intersect, then they cannot be, one of them cannot be sigma. It is easy to prove that. It's a very, very small argument because we took sigma small enough. So this intersection must contain 0, and the second line here is exactly the colorful selection of points that we need from colorful, that we need for colorful Carl-Theodori. Okay, so I guess I told you enough about KKM-type theorems. There are many more applications that I haven't mentioned. Rental harmony, which is a kind of dual to fair division. More results about fair division of multiple cakes. Game theory equilibrium, which is the original reason that Shapley was interested in proving this theorem. Results about piercing the intervals and colorful the intervals. Generalization of a colorful Carl-Theodori in a sparse way by using a sparse colorful Komiya theorem. And I will be happy if you can find other applications that are relevant to your research. So thank you.
All right. Thank you very much for the nice talk. Do we have any questions?
Yes, please. So first, thanks, Shira. It was a beautiful talk. And a question. So the theorem with Florian of this colorful Komiya. So can you find these sets of faces efficiently?
Yeah, so I will tell you where, so what is the main theorem that you need to use in order to prove this. And the question is whether you can find, so here is the, here is the main theorem. The main theorem that you use is that if you have a continuous map from a polytope to itself that is of degree 1 on the boundary, then it is surjective. And then what you do is you find the image of the point yp that appears there in the theorem. So the question is whether in this lemma, in this topological lemma that I just mentioned, you can algorithmically find the pre-image of a point. And I know that this is that there are algorithms doing that when the polytop is the simplex, or kind of in the case of Sperner's lemma or Brouwer fixed point theorem. I'm not sure if this is the case for any polytop. I'm not very strong in the algorithmic part.
I ask because it is a kind of well-known challenge to make a Barnes colorful Carl-Theodori algorithmically efficient, because there are many applications of that, Verberg theorem, etc., where it's kind of important.
Then I will look into it. I don't know. I never tried to do it.
Can I ask one more thing? You showed us this proof about using a KKM for the T3 property about piercing, and then you hinted at the very end that you have other applications to piercing problems. So can you tell us about the other piercing problem?
Yeah. So so for example, we can use say either Shapley's theorem or Komiya theorem to prove the result of Tardosh and Kaiser regarding piercing of D-interval families. So a D-interval is a union of D-intervals in R, or in, you can think of it as a union of D-intervals in R, or if you want, you can think of it of a union of D-intervals in D different copies of R, and this we call separated D-intervals. And Tardosh and Kaiser proved that if you have a family of D-intervals, then the covering number is at most d squared minus d plus 1, the matching number, where the covering number is the number of points needed to intersect all the D-intervals, and the matching number is the maximum number of pairwise disjoint D-intervals. And their proof is also topological. There is no known proof of this bound that is non-topological, but their proof, or Kaiser's proof at least, was used the Borsuk-Ulam theorem, which is considered like stronger than KKM-type theorem or KKM-type theorems. And then Kaiser, Aoni, and myself gave a proof that used the KKMS theorem, the Shapley's theorem. And what Florian and I did is just use the colorful version of Komiya to prove a colorful D-interval result. So now instead of having one family of D-intervals, you have n families, and you know that the covering number of each one of them is at least k plus 1, and you can find a colorful matching, namely one D-interval from each one of them, such that this collection is pairwise disjoint of size k plus 1 over d squared minus d plus 1, which is exactly special as to their result when all the families are the same.
Thanks.
Are there other questions? So I have a very small one.
And by the way, yeah,
sure.
I just wanted to add, Baran, that the proof is very similar to the proof of fair division with multiple cakes, because the configuration spaces are the same. So all the considerations are kind of the same in both those proofs. And as you saw there also, we had kind of like P over K squared, which is the same as the what we get here. Yes, sorry.
Yeah, no problem. I had a small question also for these transversals. So it's a bit more geometric. So are there any conditions that you can add on the sets to maybe get fewer lines? I mean, for example, if in sets, instead of sets you have points, then T3 implies piercing number 1, right? So are there any other cases?
Say again, if you have points, I haven't.
I mean, the question is just, are there conditions that you can add to the sets that you want to transverse, such that T3 implies something better?
Yes, so maybe I will answer a slightly different question. First, what we can do is relax the condition of we can ask for something less and get the same thing. So we don't have to actually ask for a T3 property. We just have to, we can show by the same proof exactly that if the sets are have what I call the TT property, which is every time you take 3 sets, they form a tight triple. And being a tight triple means that the convex hull of any two of the convex hulls of any two of the sets in this triple intersect. And you can check that if you are if 3 sets are pierced by line, then they form a tight triple. But there are tight triples that come from that are not pierced by one line. And the proof works just as well if you assume that your family has the property that every triple is a tight triple, because the contradiction we get in the set gives us 3 sets that are not even tight triple. And this is good because Holmsen proved in 2013 that if a family with the TT property that every triple is a tight triple has a line that pierces 1/8 of the elements in the family. But our theorem shows that there are 3 lines piercing everything, so there is a line that pierces 1/3 of the elements in F. And yeah, so you can ask for different conditions and then get kind of different piercing numbers. Or for example, if you have the T4 property, then you can pierce everything by 2 lines. So if you have an intersecting family, so every 2 sets intersect, then you have the T4 property clearly, because every 2 intersect and then you can put a line between them. And then you have that 2 lines pierce everything. And also if you go, I haven't mentioned that, but if you go to higher dimensions, so for say in R3, it is not longer true that the TK property will imply that you can pierce with constant many lines. But so this is an example that Alon, Kalai, Matuszek, and Meshulam gave. But there are very interesting conjectures that if you make some stronger assumption on the sets, then you can find constant many lines maybe piercing everything, or at least a line pierces a fraction of the set. So the conjecture is of Rubin, Martinez, and another one which I forget now, sorry. That if you have a family of convex sets in R3 and every 2 of the set intersect, then there is a line piercing a fraction of the size of the family. And The only known result is of Imre Baran, who proved that if all the sets in the family are cylinders, then this is true. Cylinders in the sense that they have a symmetry along a line. And I know that many people are very interested in this conjecture, and it has received a lot of attention in conferences that I've been in, but other than Imre's result. And I met Imre last week. He asked me about this conjecture, if I've given it a thought. So I know that he's interested in it, but yeah. If you want to pierce with hyperplanes instead of lines, this is another generalization, then there is a result of Alon and Kalai that give you kind of a PQ property with hyperplanes, which is, yeah, but maybe you want to find optimal bounds on these PQ numbers, so yeah. I don't know if our method go forward to higher dimensions. I haven't been able to do that yet.
Thanks. Any other questions? That doesn't seem to be the case. So thanks again, Shira, for the great talk.